Just right, so I cannot connect to the meeting. So what we'll do is that we'll keep the questions for the end, because I cannot see when you have a question from the group. And when it's time for a question, you'll just have to press escape once so that we can see basically someone who has a question.
And also people just unmute themselves. You know,
Yeah, but it can get pretty messy if there are a lot of questions. And it's, you know. Okay, yes, okay, perfect.
I'm happy to take questions.
Okay, perfect. I mean, like for people here, it's
Yes, but also because you say people find just muting and if you know, I'm anyway.
okay.
Let's get it to the
Okay, you can say okay.
upper limit is 1.
Okay, okay, perfect. No, we'll wait like for 2 more minutes and then
I see it.
all right. So thanks everyone for joining us today, despite today being part of the reading week. Today we have the pleasure to host Fred, who is a professor at the Heidelberg University, and he shared with us some thoughts on dimension reduction. So before handing the mic over to you, Fred, let me remind you all of some house rules. So as usual, clarification questions will be allowed to be asked during the talk. For people in person, it's easy. You just have to raise your hand. I'll give you the mic and you ask your question. For people online, I don't have access to the chat this time. So if you have a question, just unmute yourself and say that you have a question. If the time is right, Fred will let you ask your question directly. There'll also be some additional time at the end of the talk for people to ask a further question or have a more informal discussion with Fred here. I also know that I told you in the email that I will bring some tea and cookies. So I bought those, but I forget them in the bus. I'm sorry for that. I have some reserve upstairs, so I'll bring them after the talk. It's fine. Yes. You have access? Okay, it doesn't look like the Wi-Fi was not working for me, so okay, perfect. So Gauthier will monitor the Zoom. Thanks, Gauthier. All right, perfect. That's pretty much it for me. So whenever you're ready, Fred, floor is yours. Oh, sure.
I'm happy to not be so static. Great, Rim. Thank you very much. You made some people on the bus super happy, I think. Yeah, good morning. Thanks for coming. There's an amazingly knowledgeable audience. So the first 3 people I talked to have done either their PhD or part of their PhD on UMAP. So that's, you know, 100% quota. Very impressed. This is work, so mainly the work of Sebastian that I'm showing today, who recently defended his PhD and has now moved on to Tübingen, to the lab of Dmitry. And Nick has written most of the code, and Dmitry has given good insights throughout. All right. By the way, Heidelberg, it's a pretty place, and we're hiring a professor for foundations of machine learning. So if you're interested to hear more, talk to me. So some people in the audience, I understood, have not done their PhD on UMAP, and to those, I will now say that dimension reduction makes sense to think about, even if you're into supervised learning and such, or if you work with data, yeah, because we occasionally do work with real data, and usually we do find there's something funny that was overlooked. So either a sensor was at fault, or some people didn't respond to the questionnaire in the sense that they were meant to, and so on. And it is a good idea to look at, if you work with real data, to look at it to see if there are any funny artifacts in there. It's a bit trickier if you work with images, because it's not so easy to define distance between images. But here is some work that also is related to what I'm talking about by Nick, where he has visualized CIFAR in this case. And you can see, for example, that there are structures which correspond to duplicated cars here in the car cluster, or the horse cluster actually falls into subclusters where you have dark horses, non-dark horses, mounted horses, and so on. So even when you work with images, even when you work with other types of data, it is a good idea to try and visualize it. That's especially true if you work with tabular data. And biologists generate a lot of the kind of data that you see on the left. So in this case, we have 20,000 cells, and for each cells, the expression level of 1,000 genes were measured. And biologists, well, they love a method called UMAP that I'll talk about a lot today. And that gives you a scatter plot. So 20,000 cells gives you now 20,000 points. And all right, biologists, they usually tell themselves and tell their audience that these pictures must not be taken at face value. And then they go on about interpreting the picture for an hour or two in their when they give talks. So because us humans, we are such visual animals, it's very difficult for us to not make interpretation when we see a picture like that. So when you create that kind of picture, it's important to understand what kind of artifacts might be in there. And UMAP, I was just saying, is the biologist's favorite tool. So here is Dmitry's personal statistic of a single cell genomics conference, where 33 out of 37 talks use dimension reduction. Here's a breakdown. Basically, everybody uses UMAP. Few people use tSNE, and outliers use other methods. Somebody even used PCA. So what is UMAP? It is one of a family of methods that are called neighbor embedding methods. And it is a method that works really well. And it's a method that's not so easy to understand when you look at the original paper, because the original paper, it motivates it in terms of category theory and topology and so on. And at least to me, I have a hard time making the connection between the first part of the paper, which talks about these concepts, and then the second part of paper, which introduces the algorithm. Moreover, the algorithm or the paper gives a loss function. And if you implement that loss function, you get something that is very blurry and it looks a little bit like PCA. So what you should use is not the loss function in the paper, but the loss function in the implementation. And that loss function in implementation that subsamples the repulsive interactions. And Sebastian and myself in Europe's 21 paper spelled out the loss function that UMAP actually uses. What it does do, it builds a k-nearest neighbor graph in a high dimensional space, and then finds an embedding in typically 2 dimensions, such that those points which are adjacent, the k-nearest neighbor graph are close and the others are far. And then the original paper goes on about other things like fancy edge weights in high dimensional space and low dimensional space. It turns out those are not really needed. So if you just use the k-nearest neighbor graph with edge weights of 1, you're fine. All right, this picture explains why biologists love UMAP so much. So here you see the MNIST data. We have 10 different digits and they're color-coded. And PCA plot, it does discriminate some of the digits, but there's of course very heavy overlap. Looks a lot better if you use tSNE, and UMAP comes up with what looks like perfect clusters. They are not perfect, so some points end up in the wrong cluster, but this is pretty stunning, and I think this is what has convinced everybody in the biological community. However, if you use that, say on this example data here, so this is 2D points, and now I ask UMAP to map them to 2 dimensions, you get this. Yeah, so of course here no dimension reduction is needed. So you could argue that the perfect mapping here is just the identity, not do anything. But UMAP finds some artifactual structure. And that raises the question, of course, in pictures like these here, if this contraction or if these very compact clusters that we see here, if that is not also an exaggeration. All right, so we've spent quite a bit of time trying to figure out what these dimension reduction methods are doing, what are their artifacts. And now, of course, when you do have high dimensional data, and when you do an SVD and you find more than 2 singular values that are significantly large, you cannot hope to perfectly represent your data in 2 dimensions. There's no way you can do that. It's always going to be a trade-off, but you want to understand the trade-off. And well, it's the same data that we saw before. If you do use different low dimensional or different dimension reduction methods, you come up with very different embeddings or different pictures, and the interpretation that you're going to make of your data is going to be different in this top or in this bottom case. So we want to understand the relation in particular between these 2 most popular dimension reduction methods. Okay, and this is now the main contribution here, that we can understand the relation, and we can argue that tSNE and UMAP are just points on a spectrum, and there is a single parameter governing this trade-off, and this is now a recurring theme in this analysis. So Dmitry's lab and our lab, that was originally independent work, discovered the spectrum in terms of how strong you make the attraction or how strong you make the repulsion. And in this most recent work, which is going to come out at ICLEO this year, we explain the spectrum from a probabilistic perspective, and that's the main topic of today's talk. Yeah, so there's this parameter z bar, and depending on how you set that parameter, you get something that looks like the kind of dimension reduction that you would get from an autoencoder, maybe. You then go via something tSNE-like. So tSNE lies around here, NCViz, this implementation lies around there, UMAP lies around here, and then you can exaggerate and obtain different kinds of embeddings. They differ in structure, but they also differ. You here see scale bars, which are not normally shown in dimension reduction. And you see that they become more and more compact as we increase this parameter z bar. All right, but what is this z bar? This is what I want to talk about now. So basically, what one does is one says we have a probability distribution describing what we have in high dimensional space, and we want to match that with a probability distribution in the low dimensional space. And this probability distribution goes not over points, but over pairs of points. So let's say, consider these 6 points here. This is where the dots are. I've shown in black some edges of a hypothetical symmetric k-nearest neighbor graph. I'm also showing in turquoise all the edges of the complete graph, where each node is connected or each point is connected to every other. And we can now define a probability in this high-dimensional space, which is uniform over the edges that are part of this nearest neighbor graph, script n, and which is 0 over the edges that are from the complete graph that are not in the nearest neighbor graph. All right, and this probability distribution over edges, we try and approximate with a probability distribution over edges that is now parametrized by the coordinates of the points in the low dimensional space. So EA and EB is the embedding of point A and the embedding of point B. These are just coordinates in the 2D scatter plot that I'm producing. And phi is one of a set of kernels. What is used by tSNE is the Cauchy distribution. So it looks a little bit like the Gaussian, but it's much more heavy-tailed. And then there is some normalizing factor that we'll talk about a lot today. Okay, so if it were possible to do the embedding perfectly, then pairs of points which are adjacent in the nearest neighbor graph would, in the low dimensional space, have 0 distance. So those edges would have a large probability, and all pairs of points which are not in the nearest neighbor graph would have infinite or large distance with a probability for that pair approximately 0. But now all of this is coupled through the coordinates in the low dimensional space. Yeah, so it's a frustrated problem. It's not possible to solve it perfectly. And we're looking for the best possible compromise by matching Q to P. And when we match Q to P, there are now obviously various ways of how do you measure the distance between probability distributions. And depending on the choices you make here, you end up with different methods. All right. So I'll first give you the overview here, then walk you through some of the formula and ask you to read the paper if you want to know it in even more detail. All right. So the broad overview is that tSNE actually uses the correct normalization. We call it here partition function. So it's the sum of those kernels over all pairs of points. And for that, we need n² interactions. And this can be approximated using a noise contrastive estimation. And instead of computing here n² interactions, you can approximate this and use only a linear number of interactions. So linear in your number of points, and m is some parameter, maybe 15 or so, that you use. And here, this normalization is a parameter that you estimate in the procedure. UMAP does not estimate this parameter, but it sets it to an extremely large value, and that results in weakening the repulsion between points. And this is why you end up with more overall more compact embeddings, but in particular these very, very compact clusters. All right, and now I'll try and make a compromise between being exhaustive and giving you a little bit more than this high-level overview. All right. So in tSNE, we start and say that we want to minimize the KL divergence between the probability distribution describing what's going on in the high dimensional space and the one that gives my approximation in the low dimensional. And this is just a KL divergence, and you can rewrite it as a sum of two terms, one of which does not depend on Q at all. So this one we can ignore. And here, the kernel that's used to measure proximity in the low dimensional space is again the Cauchy distribution, the heavy tail distribution. And here the proper normalization is being used. Yeah, so here the summation over all pairs of points from the complete graph is in the denominator, and that makes tSNE very expensive, leading to a couple of approximations that people use in real life to make this work on large data. Now, in noise contrastive tSNE, which the authors have called NCVIS, the basic trick is the following. So the dimension, the density estimation problem, where we want to estimate a density, where we want to estimate a density, is replaced by a supervised learning problem. So this is almost too small to read, but what you see is a familiar Bayes theorem. And what we are really interested in this notation here is this probability of X given 1. So 1 means here that it's, right, I see something in the chat. Let me just open this. Okay, no questions so far. So I'll scribble on this whiteboard, which people on Zoom unfortunately cannot see. It's okay. It's not that important. Zoom people bear with me for 30 seconds. So I'm scribbling on this whiteboard some complicated or not density that I truly want to estimate. I'm here calling it probability of X given 1. And rather than estimating this density directly, I can compare it to some other density, which I here for simplicity, a known density, which I assume to be uniform, probability of X given 2. And now rather than estimate this class density, what I can do is I can estimate the posterior probability of having the one class versus the other. And to estimate this posterior probability, I need to draw samples from the true distribution, and I'm also drawing samples from this hypothetical, in this case, the uniform distribution. So let's say I draw M samples from the reference distribution, the uniform one, and a single sample from my true distribution. Then I know what these priors are. The prior for the true distribution is 1 over M plus 1. The prior for the uniform distribution is M over M plus 1. And this, if I cancel the terms that repeat, what I get out is this expression here, Q over Q plus M over the number of edges from the complete graph, which is a fraction that we will see throughout this page again and again. Yeah, so for example here. All right, and in this noise contrastive estimation that goes back to Gutmann and Hyvärinen 2010 and 2012, you now minimize the binary cross entropy between this true posterior and then the true probability of an edge being drawn from the k-nearest neighbor graph or from the complete graph. Yeah, and what we see here is this binary cross entropy, written down. Okay, that's the expression here. And this one still uses all pairs of points from the complete graph. So in reality, you approximate this by using only a couple of samples in each batch. And Q is now again parameterized through the embeddings between coordinates, between points, between 2 points. And it is normalized by some parameter. And this parameter is something that we optimize over in the procedure. Yeah, so the minimization here, the argmin, it goes over the coordinates of my embedding, over the 2-dimensional points, and it goes over the value of this scalar z. All right, so overall, this gives me a sampling-based approximation to tSNE. That's NCVis. Now, when we do negative sampling, here it's called neg tSNE. Rather than learn this parameter z, we fix it to some value, to some huge value. So this is the number of edges from the complete graph divided by m. It's, for large data sets, it's huge value. And otherwise leave the formula above unchanged. Or we can rewrite this. We can say that Q now is the unnormalized Cauchy distribution, and then we get here in the denominator just +1. All right, and finally, the connection to UMAP. Sorry, it was too far. Okay. The connection to UMAP is that we work with something like neg tSNE, but we're not using the Cauchy distribution, but instead we're using this 1 / distance. So a distribution which diverges at the origin here. And equivalently, you can rewrite this by using the Cauchy distribution, but then you get out this loss function here. All right. So I wanted to give you a little bit of detail here. And what we can now do is use this method neg tSNE, and rather than fix this constant z at some value like neg does and like UMAP does, we can actually scan over it. And this gives not a single embedding, but a family of embeddings that you see up here. And so the points or the plots on top have all been generated using neg tSNE with various values of this parameter z bar. And on the bottom, you see pictures that are done with proper tSNE, with proper NCVis, and with proper UMAP. And you see that they are, well, extremely similar here, only very similar there. That's because UMAP uses this diverging kernel, and on the plot here, the Cauchy kernel has been used throughout. Okay, so in words, what I've just shown you is that scanning over this parameter here gives you not a single embedding, but a family of embeddings. But let me mention a few other things. So not discussed today or not discussed in this paper, but in older work, is that this negative sampling really changes UMAP's loss function. So again, if you implement the loss function as written in the paper, you get junk. What you need is this negative sampling or this subsampling of the repulsive interactions to get useful embeddings out. And that's spelled out in this NeurIPS 2021 and in Nick's 2022 paper. Then this noise contrastive estimation goes back to Gutmann and Hyvarinen, and Artemenkov used it in 2020 to propose this method NCVis, so as a much faster way of implementing tSNE. And what we have argued in this most recent work is that that we can interpret all of this in terms of this partition function z, and that negative sampling we can then understand as learning a distribution which is scaled down. And if you look at the gradients, I've not spelled them out today, but this z appears directly in the gradients, so it gives you weaker repulsive or stronger attractive interactions. Okay, and tSNE, NCVS, UMAP, they are all intimately related. It was somehow intuitively clear before that there was a relation, but the relation was not understood. And we think we now have a better grasp of their connection. This unifying method, it doesn't roll off the tongue, but we call it neg-tSNE. And there's a Python code that you can, so Nix Python code that you can use to try this out for various values of Z. All of this is closely related to self-supervised representation learning, as Nick has explored in his upcoming ICLR 2023 paper. And maybe the most important takeaway is that you shouldn't do just UMAP or just tSNE. I think it's meaningful to look at the full spectrum of visualizations. All right, and I wanted to show you a few other things unrelated to the above that could be relevant for you. And I suggest I go over this first, and then we have questions for whatever you want, the first part or one of these subsequent parts. Or is it weird? Should we have first set of questions now? It's fine. Okay, good. All right. So I want to pitch a few ideas that maybe could be relevant for somebody in the room. So here we are working with graphs, either directed or undirected, where some nodes are marked. And we are interested in not just a single spanning forest. So it would be spanning tree if I have a single marked node, or spanning forest if I have several marked nodes. And usually of interest is the cheapest spanning forest. But here we're interested not just in this cheapest spanning forest, but in all of them, where we have a Gibbs weighing depending on the energy of these spanning forests. And and these are of course exponentially many, and it turns out that you can compute in closed form interesting properties such as the probability of a random edge or a random node here being connected to the one or the other marker. And it turns out that this goes back to results from Kirchhoff, and it's related to the random walker. And so we can compute these things, even though we can compute expectations over exponentially many of these spanning forests in closed form for directed or for undirected graphs. This one cannot be done in closed form, but we here asked if you have a source and a sink, or a S and a T node, and you repeatedly merge nodes, and you can do that in different random orders. You also end up with let's say partial assignments, and the Karges algorithm is actually one of the best algorithms to solve the min-cut problem on graphs. What we really tried to do was to solve the ST min-cut with a version of Karges. And on the one hand, it turns out that this is not possible in general, but it still gives useful distributions in practice. Yeah, so if you're interested in, if you have sources and sinks and you need fractional assignments to sources and sinks, this could be a relevant class of algorithms for you. And then we've worked for a decade and a half on unsigned graph partitioning, on partitioning of graphs where the edge weights can be either positive or negative. So signed graph partitioning. And we've worked on the full hierarchy of methods. Yeah, so solving the combinatorial problem exactly using integer linear programming, then approximate solvers that are still inspired by interlinear programs, and then cheaper heuristics like various agglomerative algorithms where we've been able to prove which of these are ultrametrics and which are not, and so on. And these are, of course, very, very fast. And they also have very different dynamics. So if you apply them on the same data, and there are some algorithms that grow one cluster after the other. So these colors here are pseudo time. And there are other algorithms with also meaningful merging criteria that somehow merge pixels or nodes all over the place without a very clear pattern. Yeah, and these are pretty good and very, very fast. And this is the problem I like. So here's an example graph. We have a node S and node T, and we have edge weights that are given by the distance here. And everybody knows the shortest path. So shortest path minimizes sum of edge weights in going from S to T. And this is what it looks like. Not everybody knows the widest bottleneck path. Here we try and make the most expensive edge as cheap as possible. And this is the path that would be used in this particular case. And you can interpolate between these two. So there's a parameter that we call R here that interpolates between these two. Then there is the commute cost distance, which explores not a single path, but all paths, and how much they are used is here shown by the edge width. And again, this is something, even though there are exponentially many paths, this is something that can be solved in closed form. It's again related to the random walker. And between these, you can also interpolate by a bag of paths framework. And all of these paths here are described by different semi-rings. And we were wondering if there is a semi-ring that generalizes all of them. And the answer is yes and no. So the structure that you see in the center of the table, this one has parameters R and mu. And for different choices of R and mu, this will specialize to any of the other distances that you see. And I like this problem because computing distances in graphs is something that you need in very many applications. However, it is not a semi-ring. It lacks the property of distributivity. So that's why it's not a semi-ring, but only a bimonoid. And the practical upshot is that you cannot use dynamic programming to optimize this. Yeah, so all of these, the white ones, can be computed efficiently, and this blue one and its specialized forms here. So this structure, it generalizes the entire table, but it can be computed efficiently only for the white fields, unfortunately. Okay, if you want to know more, talk to me or have a look at last year's ICML paper. And the last but one problem that I want to show you is this. These days I work a lot working on problems with a geometric flavor. And one of these is branched optimal transport. Yeah, so here in this 2D example, we have a couple of sources and a couple of sinks. And optimal transport says, all right, we want to get the stuff from the sources to the sinks such that distance times mass transported is minimized. Yeah, so mathematically speaking, here the cost function is the amount of mass transported times the spatial distance, and we want to get all the stuff from the sources away. We want to satisfy the demands of the sinks, and we want to not lose or gain any mass in between. So this is standard optimal transport, and this is, of course, very important in machine learning ever since this Sinkhorn light speed computation of optimal transport, which gave us a new differentiable tool in our machine learning toolkit. But you see that in terms of structure, it's pretty boring. Yeah, it transports the stuff as the crow flies from sources to sinks. What you can now do is you can add an exponent to the mass, an exponent alpha. And well, if you make alpha equals 1, you have the standard optimal transport problem. If you make it smaller than 1, what you're saying is that, let's say, shipping 1 unit of mass across 1 mile costs $1, but shipping 2 units of mass together over 1 mile costs not $2, but maybe only $1.50. And that's, of course, a property that is true for very much for the real world. Yeah, and so it's if you have a truck driving somewhere anyways, it's cheaper to take an extra parcel as opposed to sending another smaller truck for the second parcel. And so it's something that you can easily write down, but it's very hard to solve. So as soon as you make alpha smaller than 1, for alpha equals 1, it's a convex problem, can be solved efficiently. For alpha smaller than 1, problem becomes non-convex and NP hard to solve. And this is the branched optimal transport problem. And for alpha equals 0.5, for example, this would be a good solution. For alpha equals 0, we recover the Steiner tree problem. That would be a good solution. But for alpha equals 0, we completely ignore the masses. Yeah? And this creates, from a very simple formula, it creates structures that are very reminiscent of what we see in biology and in nature in general. And of course, depending on the exact distribution, there's not always a single highway going from sources to sinks. There can be a couple of highways, but these are decisions that you must make in the optimizer. So it's a mixed problem where the choice of topology is combinatorial, but then the choice of the branching points, that's a continuous optimization problem. And given a topology, we know how to solve the geometric optimization problem efficiently. Again, that can be done with dynamic programming and so on. But finding the right topology is fundamentally a combinatorial problem. So we've worked on solvers that do both. So the geometric part we solve exactly, but the topology part, for that we have a heuristic. And we get results that are too good to believe. So we find we can only solve the problem exactly for a pretty small number of nodes, because there are combinatorially many topologies to search over. But we find the global optimum or near global solutions way too often, and we still want to understand why. Yeah, and this is was published at last NeurIPS. Finally, the last vignette I have is this. So here I have a couple of points in 2D space and the minimum spanning tree. And then we perturb these points by adding just a little bit of jitter. And we get a completely different looking minimum spanning tree. However, what I would want is a spanning tree that is short, so in the direction of minimal, but I want it to be stable. So if I take the points and if I wiggle them a little, I want the tree to remain similar. And well, on the right-hand side, you see that we have already some algorithm that does something in that direction, but the proper theoretical approach still eludes us. It's still something that we are working on. And it turns out to be a surprisingly hard problem. And we're having lots of fun with this, Enrique and I. That was all. I put the email address for the people who are not here in the room today. I'm here today and on Monday. And if you would like to talk to me about any of these things afterwards, I'll be very happy to. So just drop me a single line email. And let me remind you again that there's this open position that you can talk to me about. And yeah, for now, I would like to thank you. I'm looking for your questions.
So
Thanks so much for the great talk. I had a question about one of the slides where you mentioned never trust a single visualization, but try to visualize all spectrum of these methods. My question was, why is it fair to visualize NCBIS, for instance, over tSNE when I can afford the compute? Just because tSNE is more exact with the partition function, why should I even consider taking a look at these other approximate methods?
Okay, so the question was, why use anything other than tSNE when I can computationally afford to use tSNE? And I don't think that fundamentally, the tSNE is right. There's this, there are things like, let's say, divine algorithms, or divine loss functions. To me, tSNE loss function is not one of them. So yes, using the Kobak-Leibler divergence, that makes sense, but there are many other ways. We could use integral differences between distributions, for example, or as the experts in the room know, before tSNE, there was a method called tSNE, where a different choice was made for the kernel, and that resulted in completely useless visualizations. So nobody uses tSNE. Everybody used tSNE until UMAP came along. I like to think of these methods in terms of their attraction and repulsion. And what you need is a robust function that, in the sense of robust statistics, to measure proximity in the low-dimensional space. And there is also, in robust statistics, there is not a single canonical choice for what is a robust. If you want to locate, let's say, if you want to estimate the mean of a distribution, okay, what everybody learns in statistics 101 is we do least squares. So you use a parabolic loss function. Now, if you try and use robust statistics, you use not parabolic, but something that are, you can use something like Huber or Tukey or some other potential, and there's not a single good choice for these. And similarly, I believe there is not a single good choice. Why use this Cauchy distribution and not some other distribution to measure proximity in the low-dimensional space? It's not like there are no alternatives for this. And hence, I think using tSNE is somewhat arbitrary. And all of the methods that we discussed here, except UMAP, they were still using this same function. If you change this function here, you would get a new family of visualizations. And it, I think, makes sense to certainly explore more than a single point in this space of visualizations, a single point which would be given by, for example, tSNE.
Thanks.
Thank you.
Any other question?
Hello. Could I ask you to elaborate on the choice of the Cauchy distribution? Did you try any other distributions, and did you find that this empirically worked better because of the fat tail, as you mentioned?
No, we've not tried anything other than Cauchy.
Why did you try the Cauchy first?
Okay, it's just what tSNE has been using, and tSNE, at least amongst the machine learning community, has been the gold standard for 20 years, I would say, or 10 years.
I'm curious whether you could use something like the logistic distribution instead, because that also has a fat tail. And also you have the interpretation that samples from a logistic distribution are proportional to the logarithm of the ratio between two samples drawn from a Gaussian distribution. So if you assume that you have Gaussian noise from each sample drawn from maximum entropy conditions, and if you're taking the ratio of those to calculate the distance, and that's why you have a fat tail, I'm just curious about maybe there's a potential connection.
Yeah, it's an interesting suggestion. We have not tried it, and I'm not aware if there's a paper that has done it, but it's a good suggestion. I like it.
Thank you.
One of the things that I've noticed that UMAP seem to do better than tSNE in particular, and it might have just been the Python implementation, was UMAP handles really heavily unbalanced populations well. So working with biobank data, like the UK biobank I use is something like 95% or 90% European ancestry. So tSNE really struggled with that kind of data because I found that it would artificially tear the data much more noticeably. I was wondering if you've tested any very unbalanced data sets. So something where like 90%, 95% is one class and then the remaining are split among like 10 classes.
No, I've not. And I think what you observe has to do with this trade-off of how much of the global structure do you try and retain versus how much of the local structure. But I've not played with that.
Thanks.
I have a question regarding, I think, your penultimate slide about optimal transport. I have a question about your optimal transport formulation. I have a question about your optimal transport formulation.
Oh, yeah.
Yeah,
Right.
sorry,
Great. Thank you.
I was too far from the microphone. So it's interesting because it's not exactly the standard formulation because you're allowing points to be moved. Usually you want an assignment between the red points and the blue points, but here you're allowing to move mass between the red points to create these highways, kinda. So, I mean, I guess when alpha equals 1, it doesn't change anything. You still recover the standard. They are probably equivalent, but in your case, it's very important that you can actually move.
Oh yeah, that's the whole interest. So we can still get an assignment of we can still compute let's see. All right, no, you're right. We get no assignment from that, but of course that was also not the intent.
Yes.
Yeah.
Okay. But so it seems that the constraints are still linear, yeah, and the objective is now concave, I guess. So you can show that. I mean, yeah. Basically, maybe my question is like, what are your heuristics?
Okay, so we start. So in this picture, we start from a star graph, but in real life, we start from the minimum spanning tree. In the minimum spanning tree, you have a bound that it's not worse than, what is it, twice or something? It's at most twice as bad as the optimal solution. And we then make trial moves where we reconnect edges. Yeah? So in the minimum spanning tree, I can always say that I introduce an edge, I induce a loop, I cut the loop somewhere. And we greedily, so we have now this choice of whether we want to create an edge and cut, and we make this choice greedily, and then that gives us a topology. And then for each topology, we always do this geometry optimization of where do the branching points sit, which can be done efficiently. Yeah, so that is not the concern. And so we often start from the minimum spanning tree, and then we do things like, so to say, interpolate, or when we make the changes, we've also worked with sort of compromises between the optimal transport solution and the minimum spanning tree. And what we find, so you see that we can only solve the problem optimally for 9 or 10 terminals. And here we've created, so the sources and the sinks where I put them in space, this has given me instances of the problem. So we've created many instances of these problems. And then for each instance, we see what this deterministic greedy procedure gives. And for very many instances, it gives really the optimal solution. And so here each of the light blue points is the solution that we find for one instance. Here's the ratio of the approximate to the exact solution. And very often we do find the exact solution and we're still puzzled by that fact. Okay, but my main interest here is that, like you said, the constraints are linear, given sources and sinks. It's a very clean looking, it's a easy looking formula. And then we quickly get out interesting structure. And this structure I'm interested in when, well, thinking about, flocking behavior or of course, transport of nutrients and all these things. So these kind of branching patterns we see a lot in biology.
Thanks.
And yeah.
I think one last, or I promised not more than an hour.
So I think it had been shown or suggested that many of the advantages of UMAP over tSNE stem from a smart choice in initialization function. Can you maybe elaborate how this interacts with the scaling factor that you suggested? Or
yeah, not so much. So the initialization matters and early exaggeration is a useful trick, but it's mainly more about how quickly then this converges to a good solution. I think in short, the initialization is important, but it's not decisive.
okay, thanks.
All right. No more questions? Cool. Then I'll officially end the talk. Thanks again, Fred, for this amazing talk, and thanks everyone for joining us. I wish you all a great weekend, and of course, feel free to drop Fred a line if you want to meet with him today, later in this afternoon, or on Monday. He's still here, or have a more informal discussion with him right after. Thanks again.
Thanks, Rim.